We've seen so far that it's possible to get two separate triangles that solve some given information. So in this case, alpha, or in the last case, alpha was 7, b was 5, and beta was 25. And I'm going to now change this 25 to a 75 degrees to illustrate something else that can happen. So we know the same information. We know, or actually we don't know alpha, we know beta, b, and a. And so we should be able to determine what alpha is. So let's solve for sine of alpha. Sine alpha is a sine beta over b, which will be a, which is 7 times sine of 75 degrees, all divided by b, which is 5. And if I put the right-hand side into my calculator, I see that sine alpha is equal to 1.352. There are no solutions to this equation. Remember, I suppose we could write that alpha has to be between 0 and 180 degrees. There's no solutions to sine alpha equals 1.352 because sine alpha is always between -1 and 1, no matter what alpha is. So it could never be 1.352. And the consequence of this is you would write that there are no triangles that solve or that satisfy the given conditions. So this is another situation that comes up fairly often. Let's see one more that comes up. So let's again solve for all triangles, except now a is 3, b is 5, and beta is 25 degrees. So once again, you select a law of sines that will give you one unknown, which is the same one as the previous two, and we'll write an equation. Sine of alpha is a sine beta over b, which is 3 times sine of 25 degrees, all divided by b, which is 5. And so sine of alpha is 0.254, and alpha again has to be between 0 and 180 degrees. And now for this equation, we're going to get two alphas that solve this equation. We're going to get the first alpha, alpha 1, which is the inverse sine function, so sine inverse of 0.254. And the second alpha, alpha 2, which is 180 minus alpha 1, as per our discussion earlier. Our first solution, alpha 1, ends up being 14.689 degrees. And our second solution, alpha 2, is 165.311 degrees. So we know the alpha for our first triangle and we know the alpha for our second triangle. Let's now determine what gamma is. We'll determine what gamma is by doing 180 degrees minus alpha 1 minus beta. And we'll determine gamma 2 as 180 degrees minus alpha 2 minus beta as well. What we get for gamma 1 is 140.311 degrees. And what we get for gamma 2 is negative 10.311. And so as you see, we have a negative here, and triangles cannot have negative angles. And so what we're going to do is we're just going to disregard this triangle, and we're only going to list one triangle for our solution, the triangle which has alpha 1 equals 14.689. You can even erase the subscript 1 now because there's only one triangle, so there's no subscript needed, although you don't have to. You could just list it as alpha 1. And finally, we'll use the law of sines to determine what c is. So sine gamma over c is going to be sine beta over b. But before I do that, I want to remark on a common error, and that is I see a lot of students that say, oh, now I know what a and what b are, and I want to find c. And so one thing that I see is I see students say, oh, a squared plus b squared has to be c squared. But this is not true because we do not necessarily have a right triangle. I see students try to use the Pythagorean theorem, which is what I've written, a squared plus b squared equals c squared. However, the Pythagorean theorem is only valid for right triangles. So make sure that when there's one side left, in this case c, that you're not attempting to solve for it using the Pythagorean theorem. Okay, we can solve for c. We can multiply both sides by c. These c's cancel. Then we can go ahead and divide by b on both sides and multiply, or perhaps we don't need to divide by b, that would be a bit counterproductive. We can multiply by b and divide by sine beta. So divide by sine beta, multiply by b. The b's cancel. This, what looks like a squiggle should be a c here. And the sine betas cancel, and we get that c should be b sine gamma over sine beta, which is equal to 7.555. And we can box that in, and that would give us the last measure of the only triangle, the one solution here for this particular problem.